Hello again, this is Dr. Michael Olson for Meteorology 2010 at Daytona State College. We're starting a new series of videos here for Chapter 3 from the Essentials of Meteorology textbook for the course. And this chapter will deal with air temperature. We'll begin the chapter by talking about the daily temperature cycle, as well as factors that play into daily temperature patterns. We'll also look at ways we can apply temperature measurements, as well as how to actually measure temperature in the first place. So we'll start off with the daily temperature cycle. Now, when we look at daytime patterns in temperature, one thing to note is that really each day is kind of like a tiny season. You have a season where you have a maximum heating period, summer, and a season with minimum heating period, winter. It's the same thing for a daytime cycle where you have maximum heating at noon and maximum loss of heat at midnight. Now, when we talked in Chapter 2 about conduction, convection, and radiation, we learned that air is a very, very poor conductor. Since air is such a poor conductor, then when we heat up the ground, the energy will not conduct upward very well. So as a result, just the layer right next to the ground will really get the initial conduction heating going. As a result, when we look at the temperature profile, what we'll see is the hottest temperature right near the ground, a little bit cooler up above. Now, that begs the question, at what point do we measure temperature? Because you can have 3 or 4 different people measure the temperature and all get different results based on how high off the ground their thermometers are. So we have created a standard, and that standard is that temperature should be measured from a height of 1.5 meters. That's about 5.5 feet. And that makes it a more effective and more official temperature, just so that we're all uniform and talking the same language. Other things that we need to take into account when we take temperatures, so we want to make sure it's in a good place that we're measuring air temperature, not ground temperature. For instance, when you're out over a field, you've got a lot of airflow, you can actually measure the air temperature, whereas if you put the sensor over, say, a parking lot, there will be a lot of extra heating due to the heating of the asphalt, and that would heat up the air around it. So we want to have it in a good place to measure air temperature, not ground temperature. Also, we want the thermometer to be in a shaded region, because if it's in direct sunlight, then the sunlight will be absorbed by the thermometer, thus heating up the thermometer. Now, perhaps you've driven past a field and you've seen these white boxes, such as what are pictured here. These white boxes just standing off the road look kind of like beehives or sensor equipment or something fancy. Really, it's just a miniature weather station. And it's built in this way so that it's white to reflect sunlight, and the slats in the side are to allow air to pass through, so that we measure air temperature and not just the heating of the box itself. So, air is a poor conductor. It will only heat the air next to the ground, but after a while there will be enough energy built up. In other words, the temperature will be high enough right next to the ground that air will start to move, whether through convection, lifting up higher, or through advection, being blown side to side. But this convection cycle will then help warm the rest of the atmosphere after the initial conduction begins. As a result, it takes time to actually finish heating up the atmosphere. Therefore, there's a lag in temperature, and we'll see the highest temperature not occurring at noon when you have the peak sunlight, but 3 or 4 hours afterwards, sometime between 3 and 5 p.m. Here's another explanation as to why maximum temperatures generally occur at between 3 and 5 p.m. As the sun is up, you always have incoming solar energy, and the peak energy is at noon. This is depicted with the orange line in the bottom of this figure. So that is our peak incoming solar energy. This whole time, the Earth is much cooler, and so it is emitting energy, but not as much. But while the Earth warms up, it will start to emit more and more energy until we get to a point where the incoming solar energy matches the outgoing infrared energy from the Earth. At that point, our temperature reaches a maximum. We stop gaining a surplus of energy, and roles reverse. We end up emitting more energy than we gain. We start having a deficit of energy. As a result, temperatures start to drop. And as we go throughout the night into the early morning, we continue that pattern. There's no sunlight, so all we do is lose energy until the point where we get sunrise and the incoming solar energy matches the outgoing Earth energy once again. Once that happens, you've got your minimum temperature, you've completed a daily cycle. And that is why minimum temperatures often occur about 6 o'clock in the morning, maximum temperatures sometime between 3 and 5 p.m. All right, we're ready to now talk about nighttime patterns. Because of the lower solar angle for the sun, that means we have less direct sunlight, and being more indirect, the heating becomes a minimum and it cools off. And that's kind of what we saw as we got towards evening times in the figure just prior to this slide right here. But in addition to the smaller amount of incoming solar energy, the Earth's surface will also continue to radiate and cool. As a result, since the Earth cools the quickest and the atmosphere cools at a slower rate, then because of that, the coolest temperatures will actually be near the ground and warmer temperatures just above the ground. This is what we call a radiation inversion. Now, because of this, we have the same problem. Where do we measure the temperature? Close to the surface or higher up? And we're just sticking with the same measurement. Stick your thermometer 1.5 meters above the ground. That will be the official temperature. So we end up with a situation like this. On the left side of this figure, we're showing maximum temperatures through the day, which is hottest near the ground and then gradually cooling at night, or cooling with height, excuse me. And then on the right side, we have nighttime minimum temperatures. Notice we have a nighttime radiation inversion, where it's cooler at the surface and slightly warmer above that, and then starts to cool with height. Now, we take the difference between the maximum and the minimum, and we get the daily range, which is depicted with the numbers going down the center of the building. Since the ground heats up the most and cools the most, we would expect that place to have the greatest daily range. And sure enough, that is what we see in this figure. So in this graph here, we are looking at the total, or the temperature profile near the ground, starting at 5 a.m., where you have a radiation inversion. That's the blue line on the left. At 8 a.m., because of solar heating, the ground starts to warm up. 10 a.m., by this point, the ground is much warmer, and conduction right next with the air just next to the ground starts to warm up, causing higher temperatures near the surface, cooler just above. And then noon is where you'll have the peak temperature at the surface. But at this point, because it's warmer at the surface, cooler above, you have convection that starts to happen. The surface starts to cool, but because of convection, the atmosphere continues to warm until you reach your maximum temperature at 3 p.m. And then the surface and the atmosphere all begin to cool until we reach our evening hours, where you start reforming that nighttime inversion. And there you have it. There is a 24-hour depiction of the temperature in the 2 meters just above the surface. Now we'll take a break here and do an example of something we call the thermal belt. The thermal belt happens when we have our radiational inversion, so it's cooler near the surface but warmer aloft. But in this whole profile, the thermal belt happens when surface temperatures are just below freezing, and then a little bit higher, your temperatures jump a little bit above freezing, and then the temperatures drop to below freezing again. This little band where temperatures are above freezing is known, that is the thermal belt. This is a good common example of how we use this thermal belt in the New England and other northeastern states. Often agricultural areas will not plant things down in the base of the valley, but they will plant crops rather on the hillside. The reason for this is to allow the plants to stay and have a better chance of having temperatures above freezing. All right, now we'll finish up this video talking about temperature records, and then we'll cut until the next video. Start off with high temperatures. The record high temperatures, the highest actual temperature measurement we have measured at the surface in the world happened in Death Valley, California. This was a surface temperature measurement of 134 degrees Fahrenheit. Now, bottom point on this slide, notice that was formerly held by a city in Libya, had a measurement of 136.4 degrees Fahrenheit. However, a handful of years ago, research showed that the instrument may not have been calibrated correctly. For instance, the thermometer may have only been half a meter off the ground instead of a full 1.5 meters. So, since we don't know for sure, that makes this measurement unreliable, so the next measurement that holds the record would be Death Valley. Now, when we talk about the hottest place on Earth, there's a difference between measuring one single temperature and places that are consistently hot. For example, Death Valley has the highest reading, but Palm Springs, California has high temperatures of 90 degrees Fahrenheit every month of the year, while Death Valley has some rather cooler temperatures. A couple of records on low temperature, well, that depends on how you interpret it. If we talk actual temperature measurements, in continental US, that would be Rogers Pass, Montana, of minus 70 Fahrenheit. Prospect Creek, Alaska has that for the entire United States of minus 80 Fahrenheit. And the coldest recorded temperature in the world is Antarctica, measurement of minus 129 Fahrenheit. As far as the coldest places to live, that depends on, well, how you look at it. For instance, if we look at the average annual temperature, Mount Washington, New Hampshire has an average temperature of 27 degrees Fahrenheit. That means more than half of the year, literally more than half of the year, the temperature is below freezing. We could also determine the coldest place based on the number of days below freezing, or the city that has the record number of times hitting the coldest place in the United States, as you see here. All right. That concludes the first segment of this video talking about the daily temperature cycle. When we come back next time, we'll talk about factors that affect daily temperature.